benchmark data set on that one. So in the sense that kind of everyone could play around with it. Era 5 was available and easy to use. And then a lot of developments happened, but all the time the community basically said like, yeah, it's really interesting, but yeah, it's not going to really work out because the models are just kind of, the task is too complex for those models and you only have 40 years of data. Then the Keisler paper came out, which was quite a remarkable paper where a single person could really get a forecast system built that was almost competitive in the results of our conventional models, but basically 2 orders of magnitudes faster in terms of compute time. And everyone thought, okay, wow, maybe you can do something useful with that, but it's not going to be anywhere close to the conventional model, obviously. And then all the other papers came out, and you have probably seen them, DeepMind and whatever, all the big companies, Huawei, NVIDIA did a lot of really great work, Microsoft, they all kind of published in this area, and then suddenly everyone thought, okay, well, actually, there's something in there. This really happened just basically, the DeepMind paper came out Christmas 2022, and I think you have seen a talk yesterday about all the great brokers since then. So there has been a lot of work done there. And really what's summarizing the progress for me is basically this figure here, which is from the Graphcast paper. And it's a very boring plot, obviously, but it's still extremely impactful. So you have the lead time on the x-axis, and you have the different quantities in the Earth system model and the global model at the different vertical levels in the y-axis. And whenever this plot is blue, it basically means that the Graphcast is better than IFS. So this plot basically tells you that machine learned global weather forecast system is better in deterministic prediction than the conventional model. Boom, full stop. That's the message, right? That came out Christmas 2022, and everyone thought, yeah, okay, but I mean, honestly, it's just a scorecard, right? It's trained for this. It can obviously beat the model in what it's trained for to some extent. But how do these models actually work? And if you kind of look into the details, then the first argument why these models are not very good is basically this smearing out of the forecast model as you kind of increase, as you go to kind of days into the futures in the forecast lead time. So this is a plot from the Keisler paper, where on the left side we have the truth, era 5, from the beginning of the forecast to the end, and obviously the truth is not really changing in shape, it's kind of continuing to be sharp. And on the right side, you have the Keisler prediction model, basically, and you clearly see how the small structures are smearing out. So that's a no-no for a conventional modeler, right? A conventional modeler wants to kind of represent the Earth system in all the beauty and stuff, and then suddenly the system is changing. So those models cannot really be good, right? They must be kind of fishy, and there must be something wrong with them. So a lot of questions basically popped up. Can you avoid this kind of smearing out of the structures for long predictions? Can you learn to represent uncertainties? Can you extrapolate and faithfully represent extreme events, for example? Can you represent physical consistency of the forecast? Can you actually also do data simulation? So these were the questions that basically then after the Graphcast paper in 2023, we really asked ourselves these questions. And we've done this kind of quite proactively. So what we've done at ESNWF, we basically took the models that were out and we were running them in-house. And we then kind of started to looking into the quality of the forecast on a daily basis. And we've published a paper on that in July, where we basically kind of summarize our findings. And the astonishing result is really that these models are very good. So the astonishing result is basically, I like the sentence here, the results are very promising with comparable skill for global metrics and extreme events when verified against both observational analysis and synoptic observations. So it's not just an interpolator that is doing something funny. It's a model that is really representing extreme events and weather predictions kind of quite faithfully and quite well. So that clearly showed us we need to take it extremely serious what's happening there. And also what we wanted to get is also feedback from the community. So what we also have done is we kind of took 3 of those models, and ForecastNet, Graphcast, and Pango Weather, and we are running them on a daily basis now, and we're putting the results online. And basically the idea is here that we get also feedback from the community. So the community should tell us when they see something really, really odd and something that is happening really, really badly. And they had now the chance to kind of look into this since September 2023, and we don't really get so much bad feedback there as well, right, in a sense. So we're kind of slowly building trust. And then the next steps for us was also kind of to really move into the space more aggressively, going from toy models to full forecast systems. And we, in October, basically kind of unveiled our first alpha version of the so-called AIFS. So the conventional model is IFS, so the machine learning model should be AIFS. And we're running this now basically also on a daily basis and looking into the results. And I'm not going to go into any details because I shouldn't, it's an overview talk. But we basically also now are able to kind of, well, play with the big boys in a sense that we kind of are really able to kind of get our forecast errors also into range where the other models already are. It's probably, I mean, I obviously picked the plot where we really look good. And also it's an unfair comparison because Graphcast is by now like half a year old or something like this, so it's not the latest version. But in general, I think we kind of managed to kind of get, well, gain ground if you want, and kind of basically keep up now with the tech giants as well. So, machine learning revolution, what does it actually mean? I've showed you this plot before, that's a quiet revolution. So if you compare the two things, so this is basically the same forecast accuracy that you have as in this plot for different lead times. The time scale is a bit shorter, starting from 2001. And you see kind of the quiet revolution as where the red line going up. And now you see the dark red line here, which is the AIFS. And you can see, like in particular for long forecasts, there's a jump. I mean, it's not just a small delta or something like this, but there's actually a jump in forecast quality. And it's also several years of quality, if you just continue the quiet revolution. So that's really something to look into. And that's not even kind of looking into things like synoptic observations. So I think the next step, for example, in plot like 2 meter temperature would just be to kind of train the model against like station data and stuff like this, and basically do like the model development and the post-processing in one step, and then you would probably get even better scores for some of the quantities. So there's still room for more improvements as well. What I'm going to do now is I post these questions from the 2023 on the slides, and we're going to go like through the different questions one at a time and kind of try to answer them to the best of my knowledge, basically. So the first question was, can machine learning models avoid the smearing out of long predictions, and can they also represent uncertainties? And you can basically answer this question with kind of one approach, which is that you kind of now go to probabilistic skill. If you do that, you basically want to build an ensemble, and the ensemble lives from the spread of the ensemble. So basically, therefore, you want ensemble members that do not smear out, and therefore, if you kind of can do a good ensemble, you probably can also do like long-term predictions that don't really smear out. And unfortunately, I missed the talk yesterday by Ian because I was on the train coming here, but I'm pretty sure that he talked about all these things in detail. And this is the GenCast paper, so the ensemble paper kind of based on Graphcast, and what you see there is basically the analysis on the left side. This is how it should look like, and you have different samples from GenCast with kind of 12-hour forecast prediction and the 10-day forecast prediction, and you see that the plots stay sharp. And then you kind of have Graphcast, which is smearing out, and then you have the ensemble mean from those from the ensemble members, basically as also like a mean plot that is smeared out. So you get what you expect. You get what you want to see. The ensemble members are continuing to be sharp. The uncertainty representation is as well. So if you look into CRPS, and I'm sure he's talked about all of this yesterday anyway, but also for CRPS, basically those machine learning models are competitive, if not better, than the conventional models by now. So the answer, whether machine learning models can avoid the smearing out for the long predictions and also learn uncertainty is yes, you can do that. Not a big deal. It's a data science problem. You can do that. You have to be smart with loss function and all these kind of things, but there's not a fundamental problem. Next questions. Can the machine learning model represent extreme events? And can the machine learning model represent physical consistency? So that's also a lot of the questions that are coming up, like you only have 40 years of data. In era 5, you trained from this, and now imagine there's like a 1 in 100 years event happening. What is your model actually doing? Is it just producing something that's not there? Can you trust it? Is the model actually kind of not just smearing out and not representing its extremes at all? And after looking into the results for those machine learning models for quite a while now, basically in 2023, the answer is these models perform generally quite well. So I took quite an extreme example here. It's probably kind of a bit over-optimistic for the machine learning one, but this plot is actually coming from a weather discussion. So we are an operational weather center. So we basically, every Friday, we come together and talk about the forecast quality of the model. And ever since we had the AIFS, we were also talking about the quality of the AIFS in comparison to our forecast system IFS. So on the left side, you see a control event. This is basically a situation over the US. You see the forecast error for Z850. But this event was actually kind of a high precipitation event. So basically there was kind of, due to the positioning of the jet stream, there was a high precipitation event happening here. And we didn't perform well with the IFS. So the IFS actually didn't really get it kind of quite well in the control. It didn't really get it quite well in the ensemble mean. And also the high resolution simulations from destination Earth didn't really get it quite well. So what you see is the error pattern here, and you're going to see the error is big. That's the one message you should take away. AIFS is looking quite different, and the errors are not smaller. And I mean, as I said, it's an optimistic view on the story, but basically most of the time AIFS is actually kind of remarkably similar in the error patterns as well than the IFS. But this is, for example, one example where AIFS is performing better than IFS for an extreme event. And there are many of those examples. It's not just one of them. So can machine learning represent extreme events for numerical weather prediction? Pretty much, yes. And can it represent physical consistency? Also pretty much yes, in the sense that we don't really see like a lot of problems with the model. It's not that after looking into like the results for month and month, we don't really see that the model is doing something totally unphysical for one situation out of 10 or something like this. It's really, the model is getting the dynamics actually kind of quite nicely right. So again, the answer is mostly yes. Next question, can machine learning models do data assimilation? So data assimilation is a process where we kind of bring in the observations and then we kind of put it together with a model simulation of the past. And then we generate initial conditions for the future. And it's kind of a big question because, I mean, at the moment, those models still rely on era 5. So they can't live without conventional models if you think about it. And because for era 5, you basically run a conventional model in data simulation. So the big question is, can you kind of do the whole thing and also include data simulation? Why would that not work? So first of all, it's a much more difficult task. The main reason is because era 5 is not there. So for era 5, it was just simple. Everyone can go to C3S and download the data from them. For observations, it's different. The observations are very diverse. They're coming from different sources. It's just not that there's kind of the one data set that really makes things nice. And also there's no weather bench in the sense that kind of no one is really telling you exactly what to do and kind of like to make a comparable data set yet to some extent. So the task is just much more harder because you will spend much more time in wrestling data. The further you go back in time, the less observations you have, and that's also a problem. Because basically if you go to the 80s, for example, there are not so many observations left that you can work with. And that basically means that you have to basically fill a lot of space with your model to some extent, because that's what we do in conventional modeling, right? We basically fill those blank spaces that we don't get from observations with a model. So this basically means that there's a huge null space here. So if you just start from observations and have nothing else, then you basically have a huge null space that you need to fill one way or the other, and that's a problem. And people argue that that's the reason why it should not work. There's also a problem of kind of discontinuity of some of the products. If you have, for example, Aeolus, which is one of the satellites that went up a while ago, and it's basically now at the end of business. So if the satellite just disappeared, what do you actually do then? And on the other question is, if the satellite appears, do you need to wait for a year until you have enough training data to kind of really actually use the tool? So there's kind of complexity coming up as well. One of the reasons why it should not work. But there are also good reasons why it should work. So observation operators, that's basically the process when you kind of map from observations to the model space. They are a prime example of like why machine learning is useful, right? It's kind of it's something that if you just learn to project from observations into model space, that's fantastic. So one of the components is really kind of natural. The other point is also, if you think about all the individual steps that we do in conventional data simulation, all of those individual steps should be doable with machine learning. So like, for example, run the forecast model, you could just run AIFS in data simulation that you have in 40var. You have to do minimization processes and stuff like this. You need TLID code that you can generate with machine learning. So all the individual steps you can do with machine learning. And then also we know from the generative models like GenCast, for example, that we can fill gaps actually kind of quite well and also represent uncertainties. And we know this from downscaling and also from ensemble simulation. So that's also a property that you probably need. And then last but not least, machine learning is kind of amazing in the sense that you can learn everything. So why shouldn't you do data simulation as well? There are some papers coming out. I was involved in DiffDA a little bit. So what we've done here is we basically took era 5 and then we just assumed observations are just grid columns from era 5. And then we just kind of try to learn the initial state, like the mapping from specific grid columns to the whole global fields, and then generate initial conditions for predictions. And what you see here is basically as you increase the number of columns that you observe, the error is going down for different quantities. And you can compare it with Graphcast forecasts at specific lead times, like 6 hours, 12 hours, and so on and so forth. And the result is basically that this column here is much brighter than this column here, which is good because that basically means that the data simulation is reasonably well. If you just think about a 6-hour forecast, that's yeah, it's a good thing. So in principle, you can probably do it. The results are not fantastic, and we're cheating because we're not using real observations. But there are other papers that also came out. For example, Aardvark Weather is a great example where they really did an amazing job to kind of collect a lot of different data sets and put them together. And then they basically now do end-to-end predictions as well, just starting from observations to weather predictions into the future with the weather forecast model. The results are still not as convincing as the conventional models, but in principle, they show you can do it. I mean, you can do data simulation just in general, and you can get predictions that are useful. And I'm pretty sure this setup can still be improved by a lot by using more observation data sets and also kind of a bit more, well, trial and error testing and how to do it in principle. So the answer to this question here, can models do data simulation? Is almost. So I'm pretty sure we will soon be there that we basically also get fairly competitive results for data simulation from machine learning. Okay, so I now have showed you, I don't know how many slides basically telling you how great machine learning models are and what they do better than conventional models. So now you should probably not go away and say like, okay, conventional models, we just drop them and just do machine learning only. I've also shown you this slide here. And just to make that point very clear, you can't do any of those tasks yet with machine learning models, right? So it's not that machine learning would be anywhere close to kind of have a representation, for example, of CIS cracks, to kind of get the coupling between the different model components right, to also have kind of the one tool that would kind of go from like global simulations to 1 kilometer downscaling and so on. I'm not saying it's impossible, but I'm saying we're not there yet. It's not that basically we can just kind of get rid of the conventional model itself. And just a couple of points for as kind of to think about. One of the points that I find always interesting is that we actually never really compare post-processed conventional models with post-processed machine learning models. Why is it important? Because if you, for example, have a conventional model, it will run into a certain direction, it will generate biases. Machine learning models are kind of trained to have no biases and so on. So if we want to kind of compare apples with apples, we should probably compare post-processed machine learning models with post-processed conventional models. It's a rhetorical question, people have done this, but I still want to kind of caution you a little bit in the sense, keep in mind that you still need to kind of be fair in apples to apples comparison. And then also, I mean, we had the Saharan dust event in Europe a couple of weeks ago. What's happening then with the machine learning models? I mean, they can't do it. I don't know whether they will ever be able to do it, maybe, but maybe not. Or a volcanic eruption. So just assume that in Sicily there will be a volcano going off. The machine learning models just wouldn't know. I mean, they just have no way to represent what's happening there. There's still a need for conventional models. And therefore, my take is conventional models will not be replaced by machine learning anytime soon. And also, but on the other hand, it's also really fair to say that most weather predictions will be generated by machine learning models in the future. And that's also something that is already happening to some extent. I mean, I don't know whether Google has yesterday talked about any plans of operationalization or something like this, but if you go to a weather forecast from Google and Microsoft, I'm pretty convinced that there's always machine learning happening somewhere. If it's just post-processing, I don't know, or if it's kind of already dynamically modeling, but I'm pretty sure that if you take out your mobile phone in 3 years from now, most of the forecasts you actually will look at are coming from machine learning worlds. So that's kind of the tension that we are in to some extent. Then you can ask, okay, you have the two worlds, conventional and machine learning models. So how does it work if you combine them, if you kind of put them together in what we call hybrid modeling? So hybrid models basically try to kind of combine the machine learning world and the conventional world. And you have this interesting scale because there are a lot of different approaches. On the left side, there's a conventional model only, and on the right side, there's only the machine learning model. And you can do basically attempts that are very much on the left side here, for example, the emulation of parameterization schemes. So you just emulate processes to be faster. You can do post-processing of the conventional model, doing machine learning on top of it. You're kind of still very close to the conventional model. You can do bias correction. So for example, in data simulation, you can learn biases via reconstraint Fodivar, and this will kind of bring you a little bit into the machine learning world. Then you will have deep learned biases from analysis increments. So this is basically using deep learning to literally learn a fairly complex error pattern in principle. Then you can do deep learned bias correction from analysis. So you can do like the same with Weatherbench from learning the whole model, but learning the model error. Then you can couple machine learned models to conventional components. So you could, for example, think about a machine learned atmosphere model coupled to a conventional ocean model. And you can do deep learn, for example, the whole physics part, and I'm going to talk about this a bit later. So there's a whole range of things that you can do in the hybrid world. And some of them are really interesting, and I think we should not really rule them out. We should also talk more about the hybrid world in principle. One argument that I don't buy is a lot of people say that these hybrid models will also be very useful for climate simulations, and I'm not quite sure they are, because, I mean, how many of those approaches will actually kind of be extrapolating into the future? I don't know. So does it make a difference whether the whole model is machine learning or only a small component? I don't really see why there should be a difference. So a word of caution here. I'm going to say something about this deep learn the whole physics model. That's basically work done by the Google team of Stefan Heuer. They kind of published a paper on what they call neural GCM. And the idea here is that you take a dynamical core and you basically write it into JAX, and then you can auto-differentiate through the dynamical core, and then you learn kind of what the physics would be doing, like the kind of the cloud physics and all these kind of things, by training a neural network trained against 0.5. And you kind of train it through the model. So it's kind of really nice way of kind of doing hybrid in the sense that you actually kind of put the model into the deep learning tool. And they get very good results in the sense that they can actually now run the model for what we call AMIP type simulations. So this is not just numerical weather predictions, it's actually like a 20 years running simulation that is forced by surface temperature. So it's not a climate simulation, but it's as far as you can kind of go towards climate without doing climate for an atmosphere model. And it's interesting to see what's happening because the model is performing very well again. So it's kind of performing well, for example, in the number of tropical cyclones against ERA. You have basically the same number, whereas a kilometer scale conventional models is not really getting it right. You have kind of nice biases relationships. So this is neural GCM in comparison for precipitational water. And this is XShield, which is kind of a US kilometer scale model. And you see the biases are smaller in neural GCM. And you also get the temperature response basically kind of quite well by enforcing this surface temperature. So this slide is kind of also kind of another thing to note. Machine learning can do AMIP. I mean, you can argue that's the hybrid model, but there are also now groups of Oliver Watt-Paris and others who basically also show that for conventional deep learning tools, you can also do AMIP simulations. So the next question is then obvious. What about climate simulations? Can machine learning models also do climate? Why would it not work? Extrapolation again. Every climate scientist will tell you it's not possible because you can't extrapolate with deep learning. So why would you do it? You don't even know how to represent CO2, right? These models don't know CO2. So the thing that comes closest to CO2 in those models is time. So you can basically just assume even if the model could extrapolate into the future, you wouldn't even be able to tell you something about emission. It would just do whatever it wants to do with time. You need more model components, so you need ocean, sea ice, land aerosols to kind of do a really climate simulation. You will never, ever be able to learn what the deep ocean is doing without using model data because you just don't have enough observations there, full stop. There's no end of discussion. And also, can you actually trust the model? I mean, you can run it for 100 years and get a result, yes, but I mean, conventional models you can at least believe in, but in a machine learning model, you will never know until you wait for 80 years. Why would it work? We can do AMIP simulations already. That's great. Sure, we can learn all the model components. We cannot do the deep ocean, but who can do the deep ocean? I mean, the conventional models also are struggling, and I'm not kind of want to kind of put anyone down here because I did my PhD in ocean modeling, and it's really, really painful to kind of think about how to build a numerical scheme that actually can do the deep ocean. Existing models are remarkably robust regarding unseen weather situations. So we also build trust to some extent. I mean, if they can do weather today without any kind of blunders, they can probably also do the weather in 5 years. But can they also do it in 20 years? I don't know. But there's some remarkable resilience here. And also, these machine learning models will be bias-free and beat conventional climate models. So the AMIP plot that I showed you before, climate models will beat basically all conventional models in all quantities that we have right now. And that's a big story. If you are a user of climate data and you kind of ask for the quality of the models, what does it mean? Okay. Then it basically means that you're going to have basically a model system that is unbiased and perfect in quality. So a lot of people are going to look into those, even if the CMAP community wouldn't want to look into those. And just running through the different schemes. So if you kind of think about the Earth system model in principle, The land model should be easy. Ice model should be easy. The ocean model will be difficult, but they already exist. I'm running out of time, I was told. So I just wanted to give you a couple of examples here where people have, Ian Pennington, for example, at ECNWF has looked into land modeling emulators and it's getting good results. Lorenzo Samperini is kind of looking into bias correction for sea ice and getting good results for ER5. There are also at least 2 other sea ice modelers here in the room, with Andrew, and I think Simon is also somewhere. Ocean models, we have seen the first results that kind of get good results in principle. So we will have those ocean models in principle. And also at ECNWF, we, for example, now hiring to kind of get exactly people on the ground to kind of do the ocean modeling. So that's also something that will happen in the next years. The question is kind of how to couple those models. That's an interesting question. It's not a fundamental one, but we will have to kind of think about this. And the last part that I wanted to talk about is now foundation models. Another buzzword for you. And this is a slide that I've shown a while ago, 2020 in the stone age of machine learning for weather and climate. It's not a very interesting slide. Basically shows you all the different boxes where machine learning applications had been looked into at the time. And what happened now is that those machine learning applications back then were kind of small scale applications with a gigabyte of training data and 1 GPU kind of running for an hour. But now I kind of think this further and kind of think that all those applications will actually end up being multi-node GPU applications with terabytes of data. Then we will run into computing problems. And one way kind of to address this is to think about as a foundation model. So to basically build one model that can do all those different things at the same time. And there are good approaches like AtmoRep and ClamberX. IBM is also involved with NASA, for example, to build a foundation model. So the idea is that you kind of build one model to rule them all, basically. We also have written now a proposal called the weather generator. On the EU part, it's not funded yet, but we hope that it's getting funded. But then we will also basically build one foundation model for weather and climate, and that should be applicable to like a large range of application areas in principle, like 22 applications that we have only within the proposal. So the idea here is that you basically have different data sets that coming in, reanalysis, model data, observations, and you have this kind of big general model here, and then you kind of have all these kind of applications that can kind of use this general model one way or the other. For this to make this work, you basically need to be able to kind of cater for all the different data sets that you have on the left side here. And how to do this is basically a method we call representation learning. And if you really want to talk to the specialist, you can talk to Christian Lessig, who is kind of the head behind AtmoRep. And the idea here is that you take a data set like ERA5, and then you basically produce gaps in the data set, and then you fill those gaps. So it's kind of, you don't really have a specific task that you're doing, you're just filling gaps in the data set. Now imagine that those data sets here are also different observations and reanalysis and model data and stuff like this. And once you kind of can fill gaps, you can basically also kind of go from one data set to the other. And if you want to do a forecast, you can just erase the last bit here. This is time on the x-axis, and just regenerate it. And then you have a forecast model, and so on and so forth. So you have basically a very general way of how to build those tools. The current challenges here, one of them is you want to understand how to kind of move between different orders of magnitudes from kilometer scale to global. You want to learn how to kind of build good forecast models, because at the moment those representation learning approaches typically don't tend to kind of generate good forecasts. You want to understand how to deal with complexity, because if you have a lot of input fields, you're basically going down in your HPC capacity at some point, in particular for the memory. And the compute cost is really going to be a problem. But once you've done this, you can probably kind of come up with a world like this one here. So just imagine that you had a central point to go to, let's just say one in Europe or something like this, where all the different data sets would be lying around. Observations, model data, reanalysis data, kilometer scale data from destination Earth, energy data from energy sources, whatever. And you basically would have a federated data storage that everyone could access, and you also had federated computing with it, and you had a uniform API for all the different data sets. And then assume that you had a foundation model that would actually work. So someone who wants to do machine learning could just use a foundation model that was expensive to train, and it's the big issue. And then you would basically have a fairly small tail network that would kind of take care of your specific application at the end. So it would be much easier to kind of produce a machine learning model for you. And then you have all the sorts of off-the-shelf tools for different applications like data assimilation, downscaling, and so on, where people have done this in the past, and you can basically just kind of take their network structures and so on and start from there. And all those tools would be scalable and easy to use, running on laptops and supercomputers, and all the tools are also tested with the understanding of limitations. For example, you would know whether you can trust the foundation model in climate simulations or not. This is where we should be in a couple of years from now. And to get there, we basically need worldwide collaboration, and we also need kind of very large projects, like, for example, Destination Earth, NVIDIA's Earth 2, for example, or also the project called EVE that you may have heard of, where people try to kind of generate a critical mass for the community as well. Because something like this is really difficult to do, in particular the first part where the data is going to be really, really troublesome. But then, everything is great. This is basically summarizing what's going to happen in the next couple of years. What had happened in the, for machine learning models in the last couple of years, and what's going to happen in the next couple of years. Obviously, I hope really much that no one is looking at this slide again in 3 years from now. But that is kind of at least my take of like how we are going to develop. Okay, and I think I'm going to make my session, the conveners, really angry if I talk too much. So I'll just leave it here. That's my summary slide. So we had basically the 3 different revolutions. And I think someone mentioned this morning basically that we should just not be scared too much of the machine learning models in a sense like they are actually replacing conventional models, but rather we should think they are actually a great opportunity, right? And that was the last part of my sentence that I showed you at the very beginning, that we are now really facing some rapid changes, but also this basically means that we will be able to kind of get better weather prediction and climate simulations out there. So that's a positive note for the end. Thank you.
So, thank you very much to Peter here. We have about 10 minutes for questions and plenty to get through, so thank you in advance. We'll come first, lady at the front, please.
Thanks. Is this on?
Yeah.
Oh, yeah. So, okay, with interdisciplinary research, we really have to try to define all our terms, and there's a lot of people like me that doesn't know all the weather terms. So, you know, I've been involved in a project post-processing a dynamic forecast, like a forecast from physics using ML, but you put as a challenge problem a post-processed machine learning forecast. Yeah. What is that?
I mean, basically you have, we are at a stage now that we basically get like full forecast products out of IFS and AIFS, so they would have the same format. And then the question is like, how much bias do they, for example, have? How much do you kind of have to kind of post-process the PDFs of the probability distributions, for example, with kind of statistical methods? I'm not asking for like the most sophisticated post-processing step that would then be another 3 years of research. I'm rather asking for like statistical methods that are kind of quite well known for the NWP world. And then, but once you kind of correct it for the bias, for example, you can easily get like a 20% improvements of the forecast scores of temperature, for example. So it's something that is kind of easy to do, but that we typically just ignore to do because we just, yeah, it's one more step to be done.
But I feel like from our perspective, the ML perspective, especially for doing a generative forecast, it shouldn't need, like, if it needs post-processing, we need to train a better model.
Fair enough. Yeah. Absolutely. So I'm putting this point up because I assume more benefit for post-processing to the conventional model than the machine learning model, because as you say, often we train for tools that shouldn't have biases. Having said this, some of the models actually produce biases over time, right? So if you, for example, train your model only for 2 forecast days and then you run it for 20, then you kind of can generate biases. But I mean, you have seen it on the GenCast plot, for example, that the bias is normally very small for those models. Yeah, point taken.
And when you hypothesize these foundation models, do you think we're going to get there via rollouts of short-term predictors? Or do we want to do kind of like multitask training, looking at a range of lead times? Yeah, I was cheating, right? I basically said it's a problem, but I didn't really give you a solution. I don't know. I think we will get those foundation models to become better because we will better understand to do somehow rollouts in the training. But maybe also we need to combine them with other tools. I don't know. The answer is I don't know. That's a good, for all of you guys to figure out in the next couple of years.
Thank you. I'll combine a couple of questions from online. Thank you for touching so much on the physical models of weather, for example. What kind of challenges and hopes do you see for the other components of the Earth system, for example, the oceans or the carbon system?
For machine learning?
For machine learning, perhaps.
Yeah, I mean, the challenges are different for the different components, I would say. So just take the ocean, for example. I mean, we know that it's going to be different because the timescale is different. And as the deeper you go into the ocean, the clearer it will become that you don't have the training data to actually train something useful from reanalysis. You have a lot of model data, but yeah. For sea ice, for example, I mean, you will come more into the issue, what do you trust in terms of the observation data that you, for example, have. And I mean, there are also some parameters that are under constraint, if like the thickness and stuff like this. I'm now on thin ice, literally, because a lot of bus people are in the room that will tell me off. But I think the data, you have a lot of satellite observations for sea ice, but they also kind of not always agree with each other and stuff like this, so that the truth will be a problem. For land, it's going to be fairly reasonable to kind of do this, and that's basically the three big components. The fun bit will start when you think about coupling, in a sense like would you then basically try AIFS and an ocean next to each other and then couple it, or would you put it together and do the training there and stuff like this? So, and I really don't know the answer, but I'm sure we will find an answer to that. And also my first step, at least what I would like to do in the next 2 years, is basically kind of build component models and then try to understand how we can, for example, represent the ocean in isolation. And then once we know that, we can basically kind of build the coupled models as well.
Thank you. Another question from the room, if there is one. Right at the back. Sorry to make you run, Lily.
Hiya, Harrison Cook, Australian Bureau of Meteorology. Lovely talk. I'm interested, we've seen all of these big models come out of the big tech companies, whereas in the past it's been coming from the UK Met, from you guys for IFS. What do you see as the role of the operational meteorological agencies in this changing future, or universities, where we don't have the compute to rival these big tech companies?
You mean sorry, the last bit of the question was about universities, right?
Well, yeah. What do you see the role as the operational agencies or the universities where the research has typically been done in this new tech-led space?
It's a good question. I mean, first of all, we can be grateful for the big tech to look into this in the first place, right? I mean, they showed out how things are done, and that's fantastic, right? I mean, that's kind of we really learned a lot from them. And we will continue to learn a lot from them. So I'm not saying it's really bad that they kind of come into the domain itself. On the other hand, it's kind of a bit scary, right? You have basically a domain that is kind of ruled by public entities in the past. Do you really want to trust the weather prediction, like an extreme prediction from Google? What can Google do with extreme weather predictions? I'm not saying they can't, but I don't really know how this is going to work to some extent, right? I also don't know exactly what they want to do in the future in terms of really operationalizing these kind of things. I mean, there's not such a big market in the generation of the forecast, so I really don't know what's going to happen with them, but it's just something where they played around and they will disappear again. You should have asked yesterday, speaker, rather than me. Universities, I mean, so far machine learning was great for them in a sense that you could really play around with something and kind of write a really good paper about something new. The time is kind of getting more difficult in the sense that, I mean, AIFS, for example, now we need something like 10,000 node hours to train an ensemble system. That's already on the edge of what a university could do, in a sense. So in the future, those models will become more complicated, and then it will be more difficult to kind of compete with them. It's not that different to the conventional part, though, because there we have even more compute power that we need, right? So I'm not answering your question. I'm just kind of playing around a little bit with kind of arguments. I think the foundation model will help. So you will, again, have like the big computational cost that is going to be done somewhere else, and you can just approach it. But I think we will get into a new framework where big tech companies will come up also with kind of operational predictions. I think there's enough space for the Met Office and for the Bureau and stuff like, and us, for example, to still continue what we're doing. I mean, it's kind of not that we are that expensive in comparison to what we kind of gain for the public. But it's an interesting thing to be seen. Yeah.
And perhaps one final question before we wrap up from online. Is the quality of Era 5 also subject to the improvements of the quiet revolution in forecasting? And if so, what would the implications be for using that then as training data for these models?
For So it's definitely subject to the quiet revolution, because that's kind of the developments over the time, and you see it if you compare era interim with era 5 and the next gen that we're kind of preparing right now, it's also going to be better. So yes, for the digital revolution, I'm not quite sure yet, in the sense that the developments of kilometer scale are not kind of quite there, but at some point they will become better. And who knows what we will do with data assimilation with machine learning in 5 years. So the answer is yes.
Sure. Thank you very much. That's everything from Peter. Well, thank him again.